Bismillahirrahmanirrahim. Today we are going to start second session of our lecture number 5. Before to start second session of our lecture number 5, just we will take quick overview of our first session in lecture number 5. In first session we start our discussion from thread, and we said a thread is a lightweight process. It is a process, but it is a lightweight. A one process may be divided into many threads. Okay, so when it is divided into threads, a thread must have a thread ID, program counter, register set, and stack. Okay, so we have two type of process: single threaded process and multi-threaded process. Okay, so I also given one example that of multi-threaded process. For example, in word processor, maybe a one thread for displaying graphics, another thread for responding keystroke from user if you are pressing any key. To respond to your keystroke, there is another thread, and maybe another thread for performing grammar and spelling check. So maybe this is just one example. Maybe there are more threads. As I say, maybe one thread for displaying your table, data in table. Okay, so we can divide our process in many threads. This is just for example that one process is divided into 3 threads. Why we are dividing one process into many threads? We have some benefits, so we discuss these benefits in coming slide. But before this, we have seen that each thread have minimum 5 things, that is code. What is code of that thread? What is data? What is the file? Those he need, register set, and stack. So for single threaded model, each thread have these 5 things separate. Okay, but in multi-threaded we have code, data, and files which are common, but register and stack they have separate for each. So we have discussed 5 main benefits of multi-threaded programming: that responsiveness, we have resource sharing, we have economy, we have scalability, we have less communication overhead. So we discuss these one by one, that if we are using multi-threaded programming, then multi-threading it will increase the responsiveness to the user, because we have divided our process into many threads. If one thread is blocked, it will not affect the other threads. The other threads will give response to the user, only that thread will be blocked. And also we discussed the multi-threaded web browser example we have discussed. Then second benefit that we have seen, that is resource sharing. The sharing of resource, it is easy. Threads share the memory and resources of the process to which they belong by default. So it's very easy that they can share the resources. As we discussed, code, data, and files, they can easily share with each other. Okay, then number 3 we have discussed economy. Okay, so multi-threaded system is more economical if we compare with the single threaded. That allocating memory and resources for process creation is costly. Okay, if we are going to create a process, then it is costly to allocate memory and resources. And also whenever we are going to create process, and after that we also have to manage, and manage process is also much time consuming. We need more time to manage process, to create process, and also to manage process we need more time. So we also discuss one example in Solaris operating system. If we are going to create a process, it is 30 times slower than the creation of thread. Okay, then we have discussed scalability. So benefit of multi-threading can be greatly increased in multiprocessor architecture. If we have multiprocessor architecture, then multi-threading multi-threaded programming or multi-threaded process are more better than single-threaded process. Okay, because we have more than one processor, so we can execute more than one thread at the same time. Then we have the last benefit that we have discussed, that is less communication overhead. That communicating between the thread of one process is simple because the threads share everything. So threads is sharing because they belong to same process, they are sharing different resources, they are sharing the memory address, so it is very easy that they can communicate with each other. So this was our first session of lecture number 5. So today we are going to start the second session. That first topic, that is single core and multi-core system. In recent, the system design has been to place multiple computing core on a single chip. So we have multiple processors, where each core appear as a separate processor on the operating system. We have currently system which are dual core, quad core, i3, i5, i7, they available in market. So we did not have only one processor, maybe we have more than one processor. So in this case, multi-threaded programming is more better than the single-threaded programming, as we discussed in the benefit of multi-threaded, that scalability. Multi-threaded programming provides the mechanism for more efficient use of multiple core. We have multiple core, so we can efficiently use these cores. Let's suppose in multi-thread execution on single core system, let's suppose we have only one single core. And consider an application with 4 threads, and normally we use capital T to represent the thread T1, T2, T3 and T4. So we have 4 threads. We have divided our process into 4 threads. So threads are T1, T2, T3 and T4. On a system with single computing core, the concurrency merely means that the execution of a thread will be interleaved over time, as the processing core is capable of executing only one thread at a time, as shown in the figure. Because we have only single core, only one core, one processor, so of course we have to execute all these threads. So how it will execute? Maybe it will start from thread 1, T1, after some time T2, maybe it depends, that maybe the time slice is expired and T1 time slice is expired, then we start execution of thread T2, then T2 time is expired, then T3. When the T3 time is expired, then we start execution of thread T4. When this one turn is complete, if you see, this is one turn, T1, T2, T3, T4. Maybe T1 still have some code to execute, then again we have started T1, then T2, then T3, T4, then again T1, T2, T3, T4 and so on. So in terms of time, if you see here that we have only one processor, so we are executing multiple thread on single core, on single processor in this fashion. Okay, now it will be more clear in next slide when you will see the difference between multi-threaded multi-core system. Okay, so thread execution on single multiple core system. Okay, so whenever we have multiple core, on a system with multiple core, however, the concurrency means that the thread can run in parallel. Let's suppose we have system that we have 2 cores, core 1, core 2, in 2 processors. So we will start execution of first thread on first core. Okay, so see here, we have started this first core, and then thread 2 we have given to the another processor, and then when T1 finishes work, we have given him thread 3. Here on core 2, when thread 2 finishes work, we have given the thread 4 to this processor and so on. If you see this one, in term of time, we have less time. In less time we finish more work. But if you see in single core system, we have taken more time to execute these 4 threads. But in multiple core system, we have given the threads to all the processors. Maybe we have 3 processor, 4 processor, or maybe more than this. Then same fashion we will execute the number of threads. So whenever we have multi-core system, so it means multi-threaded programming is more better than single threaded programming. Okay, now to create thread and to manage thread, we have also help from operating system, that is called thread library. A thread library provides programmer with application programming interface for creating and managing thread, because to create thread, to manage thread, this is very important task. Okay, so how we can create thread? With the help of thread library. How we can manage thread? With the help of thread library. So what is thread library? It contains the code for, we don't need to write a code how to create thread, how to manage thread. We already have one library and it consists of the code for creating and destroying thread. How we can create thread, how we can destroy threads. Also we have code for passing messages and data between thread. How we can pass any data or any message between the threads belong to same process. We don't need to write code, already we have thread library. Then how to schedule thread execution. How we can schedule thread, also we can take help from thread library. Saving and restoring thread context. Okay, so how we can save and how we can restore the thread context, we have one help, that is thread library. So it's not very difficult how to create thread, how to manage them. We already have a library that consists of all these things. For creating thread, we have help for creating and destroying thread. We have help for passing messages and data between thread, how we can pass data and message between the threads. And scheduling thread execution, how we can make schedule, because maybe we have more than one thread. So which thread we will execute first, which second, third, and so on. Then saving and restoring thread context, this also we have help, that is thread library. Okay, so we also have kernel thread. So kernel thread exists within the context of a process. In each process we have kernel threads, and provide the operating system the means to address and execute smaller segment of the process. This is the purpose of kernel thread. So provide the operating system the means to address and execute the smaller segment of a process. So how to execute the smaller segment of process? This is the kernel thread, okay, which provide the support. It also enable programs to take advantage of capabilities provided by hardware for concurrent and parallel processing. Okay, so for parallel, how we can execute more than one thread at the same time. So who is managing the kernel threads? The kernel threads are supported and managed by operating system. Operating system is managing the kernel threads. So what we understand here in this slide, in these 3 points, that with each process we have a kernel thread. Okay, so kernel thread exists within the context of process. We have kernel thread which with each process. Okay, so now we have because now we understand we have 2 type of threads. One is user thread and another is kernel threads. Okay, now we will see the different threading model, multi-threaded models. So first model that we have, it is many-to-one model. As its name shows, many to one. So in this thread
Many to one model, many user level threads are mapped to one kernel threads. Many user level threads. This is our first point, that we have in this process, in this threading model, many threads are mapped to one kernel thread. In this model, we have only one kernel thread and many user level threads. Okay, so as this diagram, if you see this diagram, it is clearly that we have 1, 2, 3, 4 user threads and only one kernel thread. So if you see this, they are connected with only one kernel thread. Okay, now thread management is done by the thread library in user space. So who is managing the thread? Thread library. Where? In user thread, in user space, here. In user space, the thread management is done. This model is efficient. This is efficient, but we have one problem. In this model, the entire process will block if a thread make a blocking system call. Here, currently we have 4 threads. Let's suppose this is T1, T2, T3, T4. If any thread will make a blocking system call, whole system will be blocked. Okay, that whole system will be blocked because because all the user level threads are mapped to only one kernel thread, because kernel thread is only one. That's why that in this model, if any thread is blocked, then whole system will block. Also, another disadvantage is that only one thread can access the kernel at a time. Okay, multiple threads are unable to run in parallel on multiprocessor system. If we are using many-to-one model, only one thread can access the kernel, because only maybe this is T1. T1 can access the kernel at a time, or there is another, suppose T2, T3, T4. So how many threads can access the kernel at a time? Only one. If T1 is accessing, then T2, T3, T4 have to wait. If T2 is accessing the kernel, then T1, T3, T4 have to wait. So this model is very efficient, very easy, but we have two main disadvantages, that if one thread is blocked, whole system will block. Okay, so this process, whole process will block. Okay, if because these threads belong to one process, that process will block if any thread is blocked. Also, another disadvantage that we have seen, that only one thread can access the kernel at a time. Multiple threads are unable to run in parallel on multiprocessors. If we have multiple processor system and we are using many-to-one model, then it's not possible that we run more than one thread in parallel. Okay, so this is our first model, that many-to-one model. Second model is that one-to-one model. Okay, one-to-one model. As its name shows, that for each user level thread we have separate kernel thread. Okay, in one-to-one model, each user thread mapped to a kernel thread. As if you see this diagram, that we have 3 threads. Suppose if I give the name to them, that T1, T2, T3. So T1 have one kernel, T2 have separate kernel thread, T3 have separate kernel thread. Okay, now if you compare this model with many-to-one model, in many-to-one we have only one kernel and many user level threads are mapped to only one kernel. Okay, and now keep in mind what are the disadvantages that we discuss. Okay, that if one thread is making a blocking system call, whole process will block. This we have discussed. So in this many-to-one, it provide more concurrency. It provide more concurrency than many-to-one model, by allowing another thread to run when a thread make a blocking system call. Let's suppose
T1, it make blocking system call, it will not affect T2 and execution of thread 2 and thread 3. Maybe T1 is blocked, okay, this kernel is blocked, this part is blocked, but it will not affect the other thread 2 and thread 3. If thread 2 is blocked, then it will not affect T1 and T3, thread 1 and thread 3. If thread 3 is blocked, it will not affect thread 1 and thread 2. Okay, so this is one benefit if we compare with many-to-one model. In many-to-one model, we have seen that this problem, if one thread is blocked, whole process will block. Okay, another disadvantage that we discuss over there, that if we have multiprocessor system, we are not able to run more than one thread in parallel, okay, at the same time. But in this model, this allow running multiple thread on multiprocessor system. If we have multiprocessor system, then we can execute more than one thread at the same time. This is the two disadvantages that we have in many-to-one model. These are overcome in one-to-one model. Okay, understand? So this is our second multi-threading model, one-to-one model. Okay, in many-to-one, more than one user level threads are mapped to only one kernel. But here in one-to-one, for one user level thread, we have one kernel thread. Okay, now we are going to discuss our last model, that is called many-to-many model. Okay, in many-to-many model, many user level threads are mapped to smaller or equal number of threads, equal number of kernel threads. Now if you see this diagram, we have four user level threads, okay, if I name them T1, T2, T3 and T4, thread 1, thread 2, thread 3 and thread 4. So in this model, that we have many user level threads mapped to a smaller or equal number of kernel threads. How many kernel we have? 1, 2, 3. So how many maximum kernel threads in this we have? We can have only 4. Okay, not more than 4, because user level threads are 4. So we have smaller or equal number of kernel threads in this model. Now, in many-to-many model, when a thread performs a blocking system call, the kernel can schedule another thread for execution. Let's suppose here we say that one thread is making blocking system call. Suppose here this T1 is blocked. So what the system will do? Schedule another thread for execution. It will not block this kernel. Okay, because this thread T1 is connected with 3 kernel, 1, 2, 3. T2 is also connected with 3. If you go back and check the one-to-one model, in one-to-one model, one user level thread is mapped to only one kernel. There is no multiplexer. Okay, so T1 is mapped to only this kernel, T2 is mapped to this kernel. If this thread is blocked, this kernel will also block. Okay, this kernel will also block. Okay, but here the situation is different. If this T1 is blocked, it will not affect any kernel. Kernels are working, but only up to this. This is blocked. Okay, so if this happen, and then it will not affect thread 2, thread 3, thread 4 and any of these 3 kernels. Okay, so in this model we have more flexibility. Okay, in this model, when a thread perform a blocking system call, any thread perform blocking system call, then kernel can schedule another thread for execution. So it means the kernel, it will not affect the kernel, only that thread is blocked. Okay, so now if we compare all these 3 multi-threading model, many to one, one to one, and many to many. So it seems that many to many model is more efficient, more better than the remaining two. Okay. Now this was our second session of our lecture number 5. We will just take a quick overview that what we discuss in today's lecture. We start our discussion from single core and multi-core system, and currently the mostly system that is available in market that are multi-core system. In multi-core system we have more than one core on the single chip, mean more than one processor is available. Okay, and then we have seen how the thread is executed on single core system, and we have discussed that suppose in our application we have 4 thread T1, T2, T3 and T4. How they are executing in term of time? Of course, because we have one processor, we need more time to execute all these threads. Okay, but if we see in thread execution on multiple core system, that in term of time it is taking less time. Okay, then we have seen thread library. Why we need thread library, and what is purpose of thread library? The purpose is to create and to manage the threads. How we can create and how we can manage, this is done by thread library. It is very easy, no need to write the code, all the code, just we can take help from thread library to create and to manage the thread. Okay, so thread library contain the code for creating and destroying thread, how we can create, how we can destroy any thread, how we can pass message and data between thread, and how we can make a schedule of thread execution and to store and restore thread contents. So these are the main things that thread library can do. And we have also with each process we have a kernel thread. Okay, and kernel threads is supported and managed directly by operating system is supporting and managing the kernel thread. Then we discussed 3 different type of model. Many to one model. In many to one model we have seen that we have many user level threads, but we have only one kernel threads, and they are connected with or mapped with only one kernel thread. Okay, this is very efficient, but we have seen 2 main problems in this many to one model. If any one thread is blocked, whole system will block. Okay, also in multiprocessor system this model is not good because we can execute only one thread at a time, not more than one. Okay, so these are the 2 main disadvantages of many to one model. In one to one model we have seen that for each user level thread we have one kernel thread, as you can see in this diagram that for each user level thread we have one separate kernel thread. Okay, now this model provide more concurrency than many to one model if we compare with many to one model, because in many to one model we have seen if one thread is blocked, whole process will block. Okay, but here if one thread is blocked, it will block only the kernel thread which belong to him, not the other. It will not affect the other. Okay, in this sense this model is better than many to one. Also we can execute more than one process more than one thread at the same time on multiprocessor system. If we have more than one processor, then we can execute more than one thread at the same time. So the 2 disadvantages that we have in many to one model that are improved in one to one model. Okay, so this is our second model, one to one, that each user level thread is mapped to separate kernel thread. And then we have discussed the last model, that many to many model. In many to many model we have seen that many user level threads are mapped to a smaller or equal number of kernel threads. This is very important, that suppose in this diagram if we have 4 kernel thread, then suppose 4 user level threads, then kernel threads can be 4 or less, not more than 4. If we have 5 user level threads, then kernel threads can be 5 or less, not more than 5. Okay, this is very important, that not possible that we have more kernel threads than user level threads. Okay, so if in this case if one thread is block, it will not affect any kernel. Kernel will schedule another thread for execution. Okay, but in one-to-one model we have seen that if one user level thread is blocked, it also affect the kernel that is mapped with that thread. Okay, but here the situation is more improved. So we can say that many to one model is more better, more efficient than many to one and one to one model. Okay, so this was our second session of our lecture number 5. Now if you have any question, you can send me email on my email address, or you can visit my office during my office hours. Okay, so see you in first session of our lecture number 6.